Every cloud you see is a colossal magic trick, playing out right above your head. It's a spectacle of physics, an everyday defiance of gravity, engineered by things so tiny we can't even see them. We look up and see these fluffy, sometimes ominous, masses floating effortlessly. But how do billions of tons of water just hang there? The secret isn't some mystical force, but a delicate ballet of microscopic particles and water vapor, orchestrated by principles we rarely consider. We're going to pull back the curtain on this atmospheric marvel, revealing the unseen architects behind every cloud. Think about it. A single cumulus cloud, the kind that looks like a cotton ball, can weigh hundreds of thousands of pounds. That's like a small herd of elephants, suspended miles above the ground. It seems impossible, doesn't it? The journey begins not in the sky, but on the ground. Sunlight warms the Earth's surface, and this warmth transfers to the air directly above it. Warm air, as we know, is less dense than cold air, so it starts to rise. As this air ascends, it encounters lower atmospheric pressure. Picture a balloon expanding as it goes higher. The air parcels do something similar, they expand. And when a gas expands, it cools. This cooling is crucial. Warm air can hold a lot of water vapor, but cold air can't. As the rising air cools, it eventually reaches a point where it can no longer hold all the water vapor it contains. This critical point is called the dew point. At the dew point, the invisible water vapor in the air begins to condense. But it doesn't just spontaneously turn into liquid. It needs something to condense asterisk on asterisk. And this is where our unseen architects come into play. These architects are called cloud condensation nuclei, or CCN. They are incredibly tiny particles, usually less than a micrometer in diameter, floating all around us. Think of them as microscopic seeds for water droplets. What are these particles made of? A surprising variety of things. Dust from deserts, sea salt from ocean spray, soot from fires, volcanic ash, even microscopic bits of pollen and bacteria. They are literally everywhere. Without these microscopic platforms, clouds simply couldn't form. The water vapor would become supersaturated, but it wouldn't have a surface to cling to and condense into visible droplets. It's a bit like trying to build a house without a foundation. Once the water vapor condenses onto a CCN, it forms a tiny cloud droplet. We're talking about droplets so small that it would take roughly 1 million of them to make a single raindrop. These droplets are too light to fall. They're so minuscule, in fact, that the slightest air currents can keep them suspended. The drag created by the air pushing against these tiny droplets is enough to counteract gravity for a long time. It's a constant, delicate balance. But a cloud isn't just one rising parcel of air. It's a continuous process. As more warm, moist air rises from below and reaches the dew point, more water vapor condenses onto existing droplets or new CCNs. This constant influx of new condensation keeps the cloud sustained and growing. And the latent heat released during condensation actually warms the air inside the cloud slightly, making it even more buoyant and helping it rise further. So a cloud isn't a static entity. It's a dynamic, ever-changing system. It's like a bustling city, constantly being built and rebuilt from within, with new residents arriving and old ones moving on. The type of cloud we see depends on a few factors: the altitude at which condensation occurs, the amount of moisture in the air, and the stability of the atmosphere. High, wispy cirrus clouds form from ice crystals, for instance. Lower, spread-out stratus clouds suggest a more stable atmosphere where air rises gently over a large area. And those towering cumulonimbus clouds, the thunderheads, they indicate incredibly strong updrafts, fueled by immense amounts of latent heat. Eventually, these tiny cloud droplets do grow larger. They collide with each other, merging into bigger drops. This process, called coalescence, is what eventually leads to precipitation. When a droplet becomes heavy enough that the air currents can no longer support it, it falls as rain, snow, or hail. The cloud then loses some of its mass, but new moisture is constantly feeding it from below. So the next time you gaze up at the sky, take a moment to appreciate the invisible symphony playing out above you. Billions of microscopic particles, vast amounts of water vapor, and the fundamental laws of physics all conspiring to create those magnificent, gravity-defying structures. It's a reminder that even the most ordinary phenomena often hide the most extraordinary science. The world around us is full of these quiet miracles if we just take a moment to look a little closer. These unseen architects don't just create beauty. They are vital to Earth's climate and weather systems, distributing water across the globe and reflecting sunlight back into space. playing a crucial role in regulating our planet's temperature. From desert dust to ocean spray, every tiny speck contributes to the grand, ongoing spectacle. It truly makes you wonder what other hidden processes are shaping our world, just beyond our immediate perception. This delicate balance, this complex interaction, is happening every second of every day, and it's a beautiful testament to the intricate workings of our natural world. What other everyday mysteries are you curious about?